Hello, everyone. My name is Dr. Ziaul Hossain, and as you mentioned, so like I am going to present the topic measuring performance of web protocol with updated transport layer techniques for faster web browsing. Now, easily we can see this is a very long title. So let me actually uh, put this title into smaller parts. So what I will do here is actually, first of all, when I say about the web protocol, so I will tell a little bit about the web protocol and what is the problem in this web protocol here. Then the second part of the title, it says about updating the transport layer. So then I will explain what does transport layer actually mean and how this actually is related to the web protocol. So web protocol, then transport protocol. And finally, when we match these two, the web protocol and the transport protocol, so how the web performance can be made better, like how the performance can be made better, we will measure that thing. So first of all, let's see what is the web protocol and what is the burstiness of the web protocol. How is it actually, what does that actually mean? So right now, if we think about all the internet applications, so there are some web applications and there are web video applications. So web video applications is almost like 69% of the total traffic, and it is even more these days. So web video traffic means like Netflix, Amazon Prime, YouTube, all these kinds of things. And then we have web traffic, which is the HTTP browsing traffic, like whenever you go to a Google web page, whenever you go to Gmail, so anything that you use the web. So we have all these different sorts of application, and these applications actually constitute most of the internet. Like among all the internet traffic, all the internet application, these are the most common ones. And these web application actually use a protocol called HTTP, Hypertext Transfer Protocol. Now, that HTTP protocol is a bit bursty in nature. So what do we mean bursty? If you think like when you normally browse a website, so what do? You first go to that website, a page comes, you read a little bit, and then you select the next button. Then you go to a next page. Then again, you read a little bit or you browse on that page, you find the information you want. Then again, you click, and then again, a new page comes. So you see, between these clicks, what's happening? You are waiting for some time. You are reading or going through this web page. So whenever you are clicking and requesting a page, a burst like this is generated, and it is being transferred from the server. So for example, from the Google, for Gmail, for YouTube, this burst comes to your computer. And this is actually a real picture. So when you normally do a web browsing, this is what happens. Like you have a data at the beginning, then for some time, there is nothing, no activity at all. After that, then there is another long data, then again no. So this behavior, we call this burstiness. Okay, like the application or data, they come in burst. Now, how is this burstiness is a problem for our computer networking? That's what we want to look like. What is a transport protocol? How does it work? And due to this burstiness, what is the problem? So we may already know that normally whenever we talk about computer communication, there is something called a layered architecture. So we have different layers. So different tasks are done in different layers in computer communication. And this is what the layers look like. So for example, from this computer on the left-hand side, you want to go to the right-hand side computer and communicate. You have these protocol layers, for example, application layer, transport layer, network layer, data link layer, and physical layer. So you have these 5 layers in the TCP IP model. You have these 5 layers, and specific tasks are done at each of these layers. Now, it is the transport layer which is actually sits in this computer and it sits on the other computer. So from your computer or between Google's computer, there is this transport layer which communicates between them directly. So this one is called end-to-end protocol. And what does this transport protocol do? Inside this transport protocol, we use a transport layer, we use a protocol called TCP, Transmission Control Protocol. TCP is important because it actually ensures that reliable delivery, that whatever data you are sending, it actually receives on the other end. So TCP maintains that. And TCP also have something called congestion control. I mean, you do not send a lot of data all at the same time. You send the data in parts. So congestion control actually maintains that. So all these are the different tasks of TCP protocol, which we use in the transport layer. Now, in TCP, we have a variable called congestion window or CWND. This congestion window is very important because it actually tells you how much data you can transmit from one computer to other computer. If the value of the congestion window is large, you can send a lot of data. If the value of the congestion window is small, the data rate is very small. But the problem is, so you may think like, why don't we actually use a very large value of congestion window? Because if you do that and everyone starts using a very large value of congestion window, no one will able to transmit because all the data, they will clash with each other and all the communication will be lost. So we should come up with a stable value of the congestion window so that we do not break the internet. Now, how does this congestion window work? So here is an example. So for example, here we have sender on this side, and sender has these packets 1, 2, 3, 4, 5, 6. These are the different packets that the sender wants to send towards the receiver. Now, in the beginning, the sender sends these first 3 packets, and the receiver then sends him the acknowledgement. He says, yes, I have received these 3 packets. Then again, sender shifts this window from 4 to 9. So instead of 3 packets, it now sends 6 packets, doubling the size because it gets confirmation that 3 packets got there. So it doubles the congestion window size, and then it sends the next 6 packets. Now, for some reason, if the receiver does not give confirmation this time that, yes, I have not received any information or I have lost some packet. So what will happen? This congestion window, this size, it will be reduced. So it will be reduced to 3. And this time I will send only 3 packets, 4, 5, 6. After sending, when I get the acknowledgement back, again, I will increase my congestion window size to 6. So this is what happens. Like the congestion window increases. If there is a loss, we do not receive the packet, the congestion window decreases. And then again, when we have acknowledgement, the congestion window increases again. So this is how the congestion window moves. So in this graph here, we can see, so all these graphs are congestion window. So on the x-axis, we have some simulation time, like with time, what happens. And on the y-axis, we have like the number of packets, like how many packets the congestion window is sending. So we can see the congestion window goes to a maximum value, then it faces some sort of a loss, then it reduces its value. Now, why do we have 3 different lines? So actually, these are 3 different TCP protocol. One is Tahoe, one is newReno, and the one is newReno with SAC. So we can see, like for 3 different protocols, the congestion window behaves a little bit differently, but most of them, they follow the same path. We call this thing the sawtooth curve. So like the congestion window increases. For example, here, the congestion window increases, it faces a loss, then again it decreases, then again it increases slowly, then again it decreases. So this is how it maintains the capacity. Like it tries to send, if there is a loss, it reduces the size. So congestion window is very important in a sense. Congestion window actually tells how much data TCP can send, and TCP then allows the application to send that much of data. So congestion window value, it actually tells the performance about the application. If it has a very conservative low value, the application performance is very low. If it has a very high value, even then the application performance is low because there will be a lot of losses. So we should have some optimum value, something in the middle. So this is how normally the congestion window works. Now, what is the problem? So this had been working, no problem. So, but what is the problem? So the problem is when there is this bursty application, then what happens to this congestion window? So let's see what happens to this congestion window. So normally this is what a bursty application looks like. So on the top graph, we have an application. So we have some burst, and then there is some idle period. There is no data to send. And then again, there is some bursts. Then again, there is no data to send, or there is very limited slow speed of data to send. So this is what the bursty traffic pattern looks like. And we have already seen that most of the HTTP traffic, it is actually bursty. So what happens to the congestion window? Now, the congestion window, this is the red line at the bottom. We can see the congestion window grows high, high, high. Then suddenly, after some time, it actually reduces its value. So if the congestion window is idle, so in the TCP, they said, if the congestion window is idle for some time, you will reduce the congestion window value. But the problem is the next time you are trying to send this data, you can actually compare, like the data is received in a very short period of time. But because of the low congestion window value, we needed a long time to send that burst. So due to we reduce the congestion window to a low value, so it is taking a lot of time. Now, also in the other case, when there is a small data traffic, the congestion window keeps on increasing, saying that, yeah, probably next time I can send a lot of data. But unfortunately, this is an invalid value of congestion window. I mean, here, if we send a lot of data, probably we will see a big loss. So this is the problem. Because of this conservative behavior here, and because of these invalid congestion window value here, congestion window does not reflect the available path capacity correctly. So there had been some work previously, like how we can fix this problem. And one of this work was CWV, congestion window validation. What it did, like it actually reduced the congestion window very slowly, rather than reducing drastically, like the previous slide we said, rather than reducing it drastically, it reduced the congestion window in several steps. But still, it had two problems. The problems was, it is a theoretical model. It actually did not tell like how to actually implement it in the practical scenario. And the other one is, if the idle period is long, very long, then still we have the same scenario of the previous one. So because of that problem, another related work was proposed, which is called TCP Jago. So TCP Jago said, okay, we will freeze the congestion window. So we will not reduce the congestion window, but rather we will freeze the congestion window for some amount of time. But it is a good solution, but still it is incomplete one, because it does not say like how to measure like what is the path capacity. So that's why, because of these two problems, CWV and TCP Jago, we came up with this new solution, which is newCWV. newCWV, we have a new variable called pipe ACK, and we use this pipe ACK value to find what should be the best value for the congestion window. So when there is no data at all, when there is an idle period, we make the congestion window half of the pipette. Or when there is in the non-validated period, so like when there is very low limited data, so we take the half of the congestion window or the initial window. So we take the maximum of it and then set the value of the congestion window in that phase. So here, what we have done, we have defined this variable pipette, which actually tells how much data has been sent or how much data that the receiver can acknowledge. So this methods for pipette calculation is actually a challenge, and we have successfully implemented that challenge. So one part of this paper was to actually implement this protocol into the Linux stack. So we actually made a Linux loadable kernel module, and we installed it into a computer in a server. And then we ran the experiments ourselves to see how practically these theory actually come. So now when we see that if we apply this method, so for example, we took new Reno, which is the standard TCP, and then we ran newCWV. So we ran two methods. So first we downloaded the applications using new Reno. Then we downloaded the websites using newCWV. And we saw that when we used newCWV, this is the improvement, percentage of improvement. So we can see if the burst size is around 4 kilobyte or 5 kilobyte, we can see there is almost like 20, there is almost 35% improvement in terms of download time. So what does that mean? That means like if we use new Reno and a web page downloads in 4 seconds, now the web page actually downloads in 3 seconds using newCWV. So this performance improvement is even more when there is a 15-second idle time. So by idle time, we meant like, for example, we download a page, then we wait for some time, we read through it, and then we press the next button. So the time in between where we do not request anything from the server is called the idle time. Now, if the idle time is 15 seconds, which is very common, like you download a page, then for 15 seconds, you read through that page, and then you press the next button. So in 15-second idle time, we can see there is almost 50% improvement if we use newCWV. That means if normally in new Reno, it would take 6 seconds or 5 seconds to download a page, now you can download that page in 2.5 or 3 seconds. So this is what it happens when you run with newCWV. So because we did not reduce the congestion window conservatively, we frozen it. So that's why the performance is very good. Now, it also has a little bit of problem. So the problem is, like if we have a congested scenario. So the congested scenario means like if there is not only one traffic, not only I am downloading, someone else is also downloading. So the network is congested. In a congested scenario, there is a little bit of performance. I mean, there is significant performance improvement here, but this performance improvement actually diminishes. It goes away when the burst size are bigger. So here in this picture, we can see like for 4 kilobyte burst sizes, we have performance improvement about from 25 to 33%, but it is actually going lower and lower for larger bursts. So because now we have a lot of traffic and all the traffic are actually sending large size bursts. So somehow it is creating a little bit of losses. but still there is improvement. I mean, the improvement is only, let's say like 10% only, for example, in this case, 1 second idle time. So there is only less improvement. There is a bit improvement, but this is less improvement. And we have already done some few experiments to find out how can we solve this problem. And we came up with a solution that yes, probably if we use pacing, another technique, pacing, so where we do not send the burst at all at the same time, but we send the burst even slowly by the technique called pacing, TCP pacing, then this performance is also improved. Now, newCWV is also, I mean, we can use newCWV with other applications. Say, for example, if we have, so if we run, for example, another application, for example, someone is downloading a file from a server, and then here we are running newCWV for downloading a web application. So then what happens? Like, can we share our network with the other traffic? Here we can see that yes, I mean, if there is the burst size is slow, and if we have then this is the performance improvement. Like for 1 second idle period, we can have 18% improvement. For 15-second idle period, it is around 20% improvement. But for larger burst size, actually it is negative. That means newCWV actually performs ORs in case there is a lot of traffic who is downloading a file. So this one, we found out this problem, and as we mentioned, like we kind of find out the solution as well. Like we have to use the TCP pacing. So we will be publishing that work with the pacing very soon. Like if we add the pacing method with it, we have found out that yes, instead of having lower performance, we can actually have better performance with it. So this is what newCWV is done. So what is this paper actually trying to do? So this paper actually says like TCP, normal TCP, they should be using a different protocol. I mean, use it with newCWV. And if we use this newCWV protocol, then it actually reduces the transfer time by around 40% for the web traffic. And for the application designers, so like how that actually helps in the real life. So whoever is writing a network program or any application designers, they do not need to worry about their application performance. Like, will TCP slow their performance? So if they use TCP newCWV, then HTTP-based application programmers, they do not need to worry, because that will make the performance similar to the application level. So this is what this paper is trying to do. Yes, so that is my presentation. If there is any question, I would be happy to